the trend of the alkali metals in water. We watched that video at the very end of class. So we've got one more slide. Oh, yeah. Talking about sections of the periodic table. And this is really how we break it up when we're regards to transition metals. So transition metals are in the middle of the periodic table, and these are interesting to us because they can exhibit multiple charges. The main group elements, which are the ones that are S and P, those always exhibit the same charge in a compound. And we'll learn how to figure out what that charge is and how it works in the next chapter. But the main group ones, so the S and P blocks, only exhibit one charge. So oxygen, for example, is always -2. Carbon is always -4 or +4. 4 there, maybe. So that's our main group. The transition metals, though, can vary greatly. So we just have to remember that property as we're going forward for those. Then down at the very bottom are the lanthanide and actinides. They're also called the rare earth elements, and these do all kinds of weird things. We won't get into why that is, but there's all kinds of interesting properties that can occur down in that bottom part. But again, this is just another way to break up the periodic table, talking about the various different sections of it. So the last part of the chapter, we're going to look at trends in the periodic table and a few basic ones at that. Now, there are entire books dedicated to this, and subjects, you can take a whole semester of chemistry and just talk about trends of the periodic table. This is a book that's over in the library, Essential Trends of the Periodic Table. It's an entire book just talking about different trends of the periodic table. 99% of the population do not find this interesting at all. I find it really interesting, actually, but that's just me. We're not going to talk about all kinds of trends by any means. We're just going to talk about a few of them that will show up as ways to explain properties later on. The first one is atomic radius. So this is how large an atom is. Atoms are larger, the bottom left of the periodic table, and smallest on the upper right. So fluorine in this area here are the smallest atoms, and then down here are the biggest atoms. The reason why that is as you go down the periodic table, so going from hydrogen to lithium to sodium and so forth, you're adding orbits to your Bohr model. And every time you add orbit, you're getting a little bit bigger. Right? You're making another level full of electrons going outwards. So as you add more electrons, you add more orbits, and therefore you're getting larger and larger. The reason why it shrinks as you go from the left side to the right side of the periodic table is because of charges. So if you think of it this way, if I've got 2 positives and 2 negatives and they are this far apart, if all of a sudden I've got 6 positives and 6 negatives, are those going to move further apart from one another or closer to one another? Closer. As the pull gets stronger, they move closer and closer. And this is what we see. As we go across the periodic table, for example, carbon has 6 positives and 6 negatives. But oxygen has 8 positives and 8 negatives. So because you have more positives than negatives, they pull together. And that's why they shrink as they get closer to one another. Well, they shrink and get closer to one another as you move across the periodic table. So this is going to come into play when we start talking about structures of materials and why they actually do what they do in regards to things like rechargeable batteries, things like that. So that's atomic radius. Does atomic radius make sense? Okay. Largest on the lower left, smallest on the upper right. you have a question?
I did. I was going to ask you, could you go back to the other side? I mean, it's okay. I'll
This one?
Yeah. It's okay. I'm just going to just, so you can keep going. I'm just going to
Okay.
put it here. You're
Okay.
fine.
The next major trend that we're going to look at is called the noble gas configuration. Now remember, the noble gases are in the 8th column of the periodic table. Helium, neon, argon, krypton, xenon, radon. Okay? These are called the noble gases because they do not react with things. It's very, very difficult to get any of them to react with something. And the reason why this occurs is because they have 8 electrons in their outer orbit, or in their valence shell. So if we count across the periodic table in terms of their valence, the first column has 1 valence electron, the second column has 2 valence electrons, 3 valence, 4 valence, 5, 6, 7, 8. And we notice that whenever we have 8 electrons in our S&P levels, that leads to extreme stability in terms of the atom. Okay? It doesn't react with things. This is called the octet rule. Okay? So things want to have 8 electrons in their outer ring. Okay? So, for example, krypton here is going to have a 4s2, 4p6 arrangement in it at this point. Okay? And because those 4s add up to 8, it's incredibly stable. And we see this time and time again. Atoms are going to react so that they pick up or lose electrons to get to this 8. So oxygen, for example, if we look at the oxygen molecule, and we draw a Bohr model for oxygen quick, we have our nucleus, then we've got 2 electrons here, and then 6 electrons here. So the octet rule says oxygen wants to get to 8 electrons. So it has 6 electrons in this outer orbit. Do you guys think it's easier for it to gain 2 electrons and get to 8, or get rid of all 6 electrons there? To gain. To gain 2 electrons. And this is exactly what it does. It gains 2 electrons to get to 8. So it gains 2 electrons to get to 8. Now, what does that do in terms of the oxygen? Oxygen starts out with 6 protons and 8 protons and 8 electrons. Then we're gaining 2 more electrons. So that's going to give us 8 protons and 10 electrons. So if each proton has a positive charge, each electron has a negative charge, what happens to the overall charge? Okay? The 8 and 8 are going to cancel out, and that leaves 2 more electrons behind. Okay? These 2 electrons are negative. So oxygen's overall charge is going to become a 2 minus, because it has 2 more minuses than it has positives. And this we see all the time. Oxygen becomes a -2 in compounds. Right? Yeah?
How do we gain the 2 electrons?
Okay. So in this case, in our discussion, we don't talk about like where they come from, but they must come from somewhere, right? We can't just magically make them. So those 2 electrons that it gains are being taken from some other atom that wants to give it up. So if we look at, let's do sodium. So sodium here, its Bohr model, you've got your nucleus. You've got 2 electrons, then you've got 8 electrons, and then you have 1 electron. So do you think sodium wants to give up 1 electron or gain 7? give up 1, right? Sounds easier to give up 1 than gain 7. Right? And that's what it does. It gives up 1. It gives up 1 electron there. And then that collapses back down to its filled shell there. Yeah?
Oh, never mind. Okay, I see what you're saying. Because we want to keep it at 8.
Yep, you want a filled shell, basically.
So you
Yep.
write down how many electrons you lost to get to 8 or how many electrons you need to add to get to 8.
Yep.
Okay, never mind. I got it.
And it does it so that it loses or gains the smallest number,
Right.
just because of ease.
Okay.
So this is going to give up 1 electron. So sodium starts with 11 protons and 11 electrons. If it gives up 1 electron, we now have 11 protons and 10 electrons. So is the charge going to be positive or negative for the sodium? What does it have more of, positives or negatives? Positives, right? It has more positives. It's got 1 extra positive. So sodium becomes a +1. And that's the octet rule. So the trend at this point is that atoms are going to react to fulfill this octet rule, the 8.
So the protons are what we need to focus on to decide how many electrons need to be added or taken away.
Well,
Because it's 11 protons, so we need to add 1 to make it to 10. I mean, not exactly add, but we need a positive charge.
you need a positive charge because there's 1 more proton than there is electrons.
Okay.
Over here in this example, where we have 8 protons and 10 electrons,
We need negative. Because
it's
we
going to
need
be negative because there's more electrons.
Okay. All right.
So for now, just recognize that they're trying to react to mimic the noble gases with their 8 in their shell. Next chapter, we're going to do a lot of this because it explains why things react. Next chapter, chapter 4, is atoms reacting together, and the reason they react together is just what I just told you here. Here we go. So chlorine, for example, chlorine is in the 7th column of the periodic table, or 17 on this board, but this has 7 valence electrons. So if it has 7 valence electrons, is it going to give up 7 electrons, or is it going to gain 1 electron to get to 8? Gain 1. Gain 1. And that's exactly what it does. So that is the noble gas configuration part of it. Now, not going to work out very well. To describe this ability to give up electrons or take electrons in, we have a property called electronegativity. Now, electronegativity is defined as how much an atom wants to pull an electron towards it. So if an atom wants to pull an electron a lot, it has a very high electronegativity. If it wants to give up an electron, then it has a very low electronegativity. This system was devised by a gentleman named Linus Pauling. And when I was going to school, my advisor at the time called him St. Linus because he was so important to chemistry. He's an amazing character in terms of chemistry. But one of the very, very rare things he did was he actually won 2 Nobel Prizes. He won 1 in chemistry for this work here with electronegativity, and he also won a Nobel Prize in peace, the Nobel Peace Prize. After the United States used nuclear weapons in World War II, he's the scientist that organized the world scientists together to kind of petition the world not to use them again. And he was the head of that movement. So he ended up winning 2 Nobel Prizes, which reminds me, Nobel Prizes are actually announced next week, I think. So we'll have a chance to talk about whoever wins the chemistry Nobel Prize and then any other ones that are interesting in regards to chemistry. So this was derived by him. Now, looking at this, you notice something very quickly. The elements that are on the left of the periodic table have a low electronegativity. They want to give up their electrons. These tend to be the metals in the periodic table. The other side, over here, have very high electronegativities. Those tend to be what we're going to call the nonmetals. So metals of the periodic table are on the left side. I get confused between right and left sometimes. On the left side of the periodic table, so all of this are metals. All of this is metals. And then over here, this is nonmetals. So metals are to the left of this line I put on the board, and nonmetals are to the right. Metalloids are halfway between the two. If a metal is shiny, a nonmetal is not shiny, a metalloid is kind of shiny. Metalloids are the ones that are touching the line itself. So boron, aluminum, silicon, germanium, and so forth and so on. They don't have aluminum marked there as a metalloid, but I think that's a mistake on their part. It acts more like a metal because it's on this side, but it's touching the line, so it technically is a metalloid. So anything touching the line is a metalloid. Then metals are to the left, and nonmetals are to the right.
So the ones at the bottom, they are
Metals. Yep, because they actually sit right here, so they're well within the metal range.
Okay.
So if I close my eyes and I point, selenium, is that going to be a metal or a non-metal? Non-metal. Non-metal. If I aim this way a little bit, tin is going to be a metal. Because of this, you know some properties of them. A metal. Are metals shiny? Yes, they are. So tin is going to be shiny, selenium is going to be not shiny. Tin is going to conduct electricity, selenium is not going to conduct electricity.